All right, so the way that these work is it looks really confusing, but at its most basic is you're basically just going to see what signals are close to each other. In other words, remember how the splitting was based on number of nearest neighbors, right? Well, the number of nearest neighbors is based on what's called coupling. You can only have protons or atoms coupled to other atoms if they're similar in terms of energy and environment and also close to each other physically. Spatially might be a better way to put it. Right, so if you look at this, this is an example of what's called cozy NMR, which we'll go over in more detail in a second. But basically, if you look at the top, you get a one-dimensional NMR. So regular proton NMR. And if you look on this side, you also get a one-dimensional NMR. So really what this is doing is it's going to see, okay, which peaks are close to other peaks or are coupled with them somehow. And so normal NMR spectrum they call it one-dimensional, even though the peak, you can count the peaks as being two-dimensional. We're talking about what variable we're controlling, what's our independent variable. And so the two-dimensional NMR has two frequency dimensions, meaning two of these ppm dimensions, the parts per million. And the way that this works is normally in NMR, you have something that looks like this, where we put our sample into the NMR, we spin up the magnetic field and let everything kind of fall into place, and then we hit it with some radiation, and then we look at what the signal is that it then gives off as it relaxes back again, right? And so this is going to be gradually coming down this oscillation. It's called a dampened oscillation. It doesn't repeat infinitely because eventually it gives off enough radiation, enough light, that it goes back to everything being in the ground state. Which, if you remember how NMR works, we basically just put everything into a giant magnetic field, and then that gives us two states. We can have our magnetic field of our protons either facing with the magnetic field or against the magnetic field. And with the magnetic field is going to be lower energy. Against the magnetic field is going to be opposite. It's going to be higher. Right. So what this pulse is we hit our sample when it's all relaxed. It should all be in the ground state where it's all going with the magnetic field. And when we hit it with the right frequency of light, we can get it to jump to the other energy state where it's going against the magnetic field. And then when it falls back down, it gives off light again. Right, so that's what's happening in this data collection phase. We basically put everything in that magnetic field, hit it with a whole bunch of light so that everything goes to its excited state, and then watch it really carefully as it settles back down. Because this dampened oscillation is slowly giving off radiation in just the sense of light. What 2D NMR does is it basically does two pulses. So before you give it a chance to fully relax and before you start collecting data, you basically just added a gap in between these two things. Right, and so that's basically going to, and then we can take that data that now looks like a couple different waves on top of each other. How much physics? You didn't talk about Fourier transforms in physics yet, did you? Probably not at all for trig-based physics. I don't think they really get to that till third year physics anyway. Basically, a Fourier transform takes raw data Right here, sir. Thank you. A Fourier transform takes data that looks like two waves on top of each other. If you have two waves on top of each other, like let's say that we've got a slow wave and then we add a fast wave on top of it or a high frequency wave on top of it. If we add those two things together, we're going to get something that looks like something like that, right? Where you get the constructive and destructive interference. What a Fourier transform does is it takes the messy wave that looks like two signals on top of each other and it turns them back into being two separate waves. It's just a mathematical operator. It's really, really, really useful in physics and in chemistry. All right, so that's all that this is showing. This arrow is just representing, we get this really messy data when we do a 2D NMR, which we can then turn it into something that looks like this. Right, and typically what you see is you're going to see that the 1D NMR on the x-axis and on the y-axis, and the little dots here, sometimes you'll see them color-coded. It's a heat map, because really what they're showing, that's probably more common now. These slides are now 10 years old, probably, if not older. So what it exactly looks like might change a little bit. But these are basically just representing that we have a signal there and they're coming out of the board towards us. So they're kind of like a topographical map. That's what I have a zoomed in version on a few slides from now. All right, so again, the most basic version of a two-dimensional NMR is called COSY, correlation spectroscopy. To get a little bit lazy with the acronyms to make it so that you can say it as a word. Yeah. And all it's really going to show us is what protons are close to each other. So let's look at an example. So if we have this molecule here, there's three distinct protons. The molecule has some symmetry, so if there's some other carbons on here, but they're not going to show up because they're identical protons, right? So we have methyl protons, the nitrogen protons, and we have the CH2 protons. If we're trying to actually figure out which of these signals go with which, we can just do it by looking at what the chemical shift is and the integration. That's going to help for all of this. But when we do a COSY NMR of it, we're basically just going to see two signals. We're going to see signal A coupling with signal A. And we're going to see C coupling with C. A and C can't be coupled together because they're too far apart. And A can't be coupled to B and C can't be coupled to B because it's attached to a different type of atom. So remember how we don't see splitting with alcohol hydrogens? They might show up on our NMR, but they would never show any splitting because the energy of the oxygen is too different than the energy of a carbon-hydrogen bond. So we only have two signals in our 2D NMR. And they're always, when you see something coupled with itself, like A couples with A and C couples with C, they're always going to show up on the diagonal. Because they're both the same distance away from zero, right? So they're always going to be, it's going to look like a one-to-one line in mathematical terms. Right, so anything that's on the diagonal is not going to be really useful. Basically, if you took the signals that show up just on the diagonal and you did a Fourier transform of them, you would get a one-dimensional NMR back. because it's just those coupling with themselves. So let's look at a more interesting molecule. So this one doesn't have as much symmetry. So how many different signals would we expect to see? All right, how many distinct hydrogens do we have here? Yeah, we've got the methyls. We've got the CH2 that's closest to the methyls. We've got the CH2 that's further from the methyls. And then we've got the nitrogen, which shouldn't show up as being coupled. So we should see 4 total peaks here, which we do. And if we zoom in on them, this is a simple enough molecule, we don't need 2D NMR to figure this out, right? Because we know just based on the chemical shift and the splitting, we know that these two have to be these ones, right? And then we've got a big peak here that's got 3 times as many hydrogens. This is another way of showing the integration. It's just with the red numbers below. So we've got a CH2, something that's broad, not coupled to anything else, that also has an integration of 2. So what is that one? It's going to be the nitrogen, which means this one that's got 3 times as many hydrogens has got to be our methyls. Exactly what we expected. When we do the 2D NMR of this, though, we still see our diagonals. And the bigger the molecule, the more obvious it is where the diagonals are, right? And then these ones on either side of the diagonals are what's interesting in a 2D NMR. And the way that you interpret that is you basically look at this, you follow this down from the 1D NMR and say, okay, what's lined up with this peak? Even if we don't know what these letters are yet, we can say, okay, well, I've got this peak here. And when I follow it straight down, I get a peak with it bonding with itself or coupling with itself, which is not interesting. But then also with this peak C. So what that tells us is that B and C are next to each other. Right, so think back to when we were doing our proton NMR and we're trying to think, well, I know I've got 2 CH2s and I'm going to guess that this CH2 belongs to this peak and this like we got to a point where we couldn't really definitively say, we just had to use our best judgment and electronegativity. This is basically removes the guesswork from it. Because you can 100% say peak B must be really close to peak C. And peak D is not coupled with anything. Right? If I draw a line straight down here, D does not have anything besides itself. And A doesn't even show up on this because it's a nitrogen. Right? So this tells you that D is not coupled with any other nearby protons. It either doesn't have any neighbors or it's next to something else.
How do you know that there's 2 D? Like there's 2 methods. How do you know that there's 2?
From the integration and from the molecular formula. Remember, we usually know what the molecular formula is for these, and we try to figure out. Yeah, I'm not usually going to give you one of these by itself with no context.
Okay.
Right, and so when you're interpreting these, one of the first things you might want to do is actually get a piece of paper or a ruler and draw your diagonal. It makes it really obvious what's lined up with what. Because otherwise, I'd be looking at this like, oh, is that itself? But as soon as you put the line through it, it's really easy to see. And we really only need to look at one side of the line, right? Because you're going to get a mirror image on both sides of it. which makes sense, right? Because if B is coupled with C, then C is also coupled with B. Right, and here's what the zoomed in, if you zoom it in further, you get something that looks like this, more like a topographical map now that we can see a little bit of details. Here's our diagonal. Here's B coupled with C. Here's C coupled with B. So there's our diagonal couplings. B coupling C, C coupling with B. All right, so let's make it a little bit larger. Basically, same molecule, we added one more CH2 in the middle. So now we should see something that's a little bit more interesting, right? And again, we can interpret this one on our own. There's our nitrogen. That's a CH2. That's a CH2. That's a CH2. We could guess what the order is going to be. We know that this one is going to be our methyls. What is going to be the most shielded of these CH2s?
I feel like the one in the middle, because the other two are so close to the nitrogen.
Yeah, that would make a lot of sense to me as well, right? We'd expect this one to be this peak right here. It's the most shielded. Then these two others, okay, out of these two, which one is going to be more shielded?
The one that is by the middle.
You think this one's more shielded?
Yes.
Why?
Because there's just less interactive.
Correct. There's less over here. Shielding is another way of saying electron density, right? More shielded has more electron density. Yeah, because these methyls are electron donating. Now that we have that language, that makes that a lot easier to think about. So we would expect this carbon to be probably the one closest to the methyls.
Okay.
B is the most deshielded. C is the most shielded. So we did get it right.
Mm-hmm.
Here's what our 2D NMR looks like. Right, so C has two nearest neighbors, right, or two carbons. So it has four nearest neighbors. C, we would expect C. C is coupled to B, and C is coupled to D.
Yeah.
B is only going to be coupled to C. D is only going to be coupled to C. Would be what we expect to see, if we're understanding this properly. So there's our 2D NMR, our cozy NMR. Put our line on it.
Yeah, the B.
Right, here's the zoomed in version.
It's like to the surface we have, like anything wrong with that. Yes.
It's going to be tied to the coupling. You can kind of see it if you in the zoomed in version. There's 1, 2, 3, 4, 5. And this looks like 1, 2, 3, 4, 5. And on this way though, there is information there, but it's a little bit trickier to interpret, and you don't usually need to. Usually, we understand splitting pretty well when it comes to a 1D NMR. So there's not really a need to do it there. Just look at this as a group of peaks. All right, and so we can see, okay, C is coupled to D. We expected that. We also expect C to be coupled to B, which is what we see. We don't see B coupling to D. So B has just one signal off the diagonal. D has just one signal off the diagonal. C has two because it has two sets of protons it's coupled with. Right, so the diagonal, and get out a ruler and draw straight lines and see what's next to what is going to be one of your best ways to do this. And just because we have this doesn't mean we ignore our 1D NMR. Our 1D NMR is still easier to understand. Right, especially since we have so much more practice with it.
Yeah.
This just allows us to really, instead of guessing like we did before, oh, I think C is the one in the middle. The most de-shielded or the most shielded is the one in the middle. This proves it.
Yeah.
So let's make it more complicated. With HSQC, heterosingular quantum coherence spectroscopy. And what that means, heteronuclear means we're looking at carbons interacting with protons. So basically, this is now looking at the coupling between a carbon and a hydrogen instead of hydrogens and the nearest neighbors. So in other words, you're going to take your proton NMR and your carbon NMR. And this is going to allow you to link and say, okay, this carbon is tied to these hydrogens. Okay, so when you remember talking about carbon NMR, all of our carbons showed up in carbon NMR, right? But protons, carbons that had protons only showed up in proton NMR if they had protons. Right, so anything that's in the carbon NMR that is not coupled to anything else must not have any hydrogens on it. So basically what these signals are going to be showing is a carbon that is attached to, or hydrogens that are attached to carbons. All right, so let's go through an example. So here's our carbon NMR for the same molecule we looked at once already, right? This is our simplest one. Our carbon NMR looked like this. We only have two peaks labeled. This is probably solvent or something. And when we did it with it, remember the DEPT?
Yeah.
Remember that it's CH and CH3 show up as an upward peak, and CH2 show up downward, and carbons with no hydrogens don't show up at all. So that right there is enough for us to label these carbon peaks, right? Because we've got a CH3 on A. B is not going to show up because it's not a carbon at all. And C is CH2, so it's going to be pointing downward. When we look at the HSQC for this, see, okay, well, A is coupled right here. It's the first peak in the proton NMR. I'm going to go back for a second to look at the proton NMR. A was our first peak there, right? So this one, HSQC, we don't draw the diagonal. Carbon NMR. Right, and so this is just a way that you can directly translate between proton and carbon NMR. This gives us a one-to-one way we can look at this. Say, okay, this peak is carbon C. That tells us this NMR or proton peak has to be the protons that are on C. So it's almost like a foreign language dictionary. It gives you a one-to-one. This carbon means this hydrogen. Or this peak on the carbon NMR means that peak on the proton NMR. Right, so these ones, there is not going to be a diagonal that you draw a line through and ignore it. You drop your perpendicular and your horizontal lines. Okay, that's my carbon A. Here's proton. So let's do the more complicated one. So here's our carbon NMR. And again, it's the same 3 peaks, almost guaranteed that solvent. Maybe this is in toluene or something. They're up in the aromatic area. Doesn't matter. We have our peaks labeled here. If we look at a DEPT, we should see D should be pointed up. B and C should both be pointed down, right? So we have one CH3 and we have two CH2s. Which is what we see. That's enough right there. So we can say, okay, well, I know this one at 45.68 has to be my carbon B. But that still makes it a little trickier for B and C. So when we look at our HSQC now, we can say, okay, well, and even have it zoomed in. Here's the one we labeled it as, this middle one was one we labeled as D. And it shows up with a nice big spike right here, directly underneath our big broad peak here. So that allows us to say this is definitely D. But these other ones, we're trying to determine between B and C, what goes to what. It's a little bit trickier. We would expect to see the more de-shielded is going to be B when it comes to the protons, right? But carbon NMR doesn't follow our same rules for shielding the same. So we kind of go back to our training wheels, which was proton NMR. Proton NMR has a ton of information and say, okay, well, I'm pretty sure that this is the proton peak that goes to B because it's the most de-shielded. C should be more shielded because of these methyl groups. So that means this is my carbon NMR peak that's associated with carbon B. All right, one more. Let's look at our last more complicated one. We now have 4 different carbons. So 4 peaks here, plus our solvent. All of them except for E are CH2s. So 3 peaks point down, 1 peak points up. So that means once again, and it actually even happens to be the exact same number. That's rare. But that kind of makes sense because these methyls are going to have almost identical chemical situation to the methyls on this molecule, right?
Yeah.
So it makes sense it'd be really similar. It's just odd that it's exactly the same within sig figs, but hey, we'll take it. B, C, and E, or B, C, and D are going to be a little bit trickier. But we know we can assign them according to the proton NMR. So we come in here and say, okay, well, here's C. C is our most shielded. Boom. That allows us to tie these together really, really well. And here's our zoomed in version. We know E is correlated with E, but then we got our most de-shielded proton gives us an answer for our carbon NMR. And there's D. E is the one we expected it to be. And there's C. So what this is giving us is basically if we do this in sequence, we take a proton NMR, we take a COSY a 2D proton NMR. Between that, that's enough to fully identify without any question what all of our peaks are in the proton NMR. Then we can take that and do an HSQC and say, okay, now that I know without a shadow of a doubt what my proton NMR looks like and assign peaks to the molecules, it basically makes it a lot easier to interpret the carbon NMR as well. It gives us a procedure instead of hand waving a little bit and being, I'm pretty sure, but right? All right, I think this is the last one. This is the trickiest one. Heteronuclear multiple bond coherence spectroscopy. Heteronuclear, so we're still going to be comparing carbons to hydrogens. But where HSQC looks specifically at just what protons are attached to what carbons, this shows correlations when you've got protons and carbons that are 2 or 3 bonds apart. Not 1, not 4. So this one's not going to show us what hydrogens are directly attached to carbons. It's going to show us our nearest neighbors. And once again, it's going to be our proton NMR on top and our carbon NMR on the side. But now instead of, so the same molecule, we already have these peaks, the carbon NMR and the proton NMR fully identified. But now it's going to say, okay, well, if we do an HMBC, that allows us to say, okay, well, this carbon or this proton is correlated with this carbon. So it must be either 2 or 3 bonds away. This proton, so in other words, the hydrogen that is on C is 2 or 3 bonds away from a carbon A. And so if we count it, we actually say, okay, there's my carbon, nitrogen. So this is carbon C. The proton on carbon C, 1 bond, 2 bond, 3 bonds. So it's correlated here. We're not looking at proton nearest neighbors. We're looking at a proton to a carbon that's exact range of 2 or 3 bonds. So it's not going to show it as correlated with itself. And it's not going to show up as being correlated with anything further away. Right, so our proton at 2.41, which is our methyl, should correlate to carbons 3 bonds away. So here's our methyl hydrogen, 1 bond, 2 bond, 3 bonds. So proton A is correlated with carbon C. And proton C is correlated with carbon A, 1, 2, 3 bonds away. There are no carbons 2 bonds away. And this won't work with a nitrogen. Because remember, for NMR to work at all, we have to have an odd number of particles in the nucleus. Nitrogen has 14 particles in the nucleus, so nitrogen won't show up in this at all. Why is C still showing up coupled to itself though? I just told you that it has to be 2 or 3, not 1.
If it's. No, because they're next to each other.
You're both right. You both said the same thing. You disagreed with each other, but you said the same thing. Because that's not going to show up as a separate signal in the proton NMR. The carbon NMR, it's the same carbon. They're chemically identical. But it means that this hydrogen carbon or a hydrogen C, 1 bond, 2 bond, can couple with carbons. I didn't finish drawing.
It's not.
It's this carbon. Right, so normally you won't see the protons on a carbon coupling with the same carbon signal unless you have high degrees. So that should go away when we look at our next molecule. And so we have C coupling with C, and we have C coupling with A. So proton C has 2 carbons that are either 2 or 3 bonds away. Carbon C has 2 sets of protons that are either 2 or 3 bonds away. So let's get rid of the symmetry, since that made things actually a little bit more complicated, it seemed like. All right, so here's our molecule here. We already assigned B, C, and D in the protons, and B, C, and D on the carbons. Our proton at 2.75, that's B. That's the one that's drawn right here. It should show up as there's going to be a carbon 2 bonds away. There's no carbon 3 bonds away. So B should only have a single, proton B should only have a single signal here. Just that one. Just carbon C. Which is what we observed, right? Proton D is going to be so this is for C. We'll go in the order that the slides go. We'll get to that one in a second. C should be more complicated because this proton has 2 bonds away. It gets the carbon B. 1, 2, 3 bonds away. It gets the carbon D. So it should have 2 signals show up, not to itself at all, though. Right? So C, we have a signal for B and a single signal for D, and nothing. And the figure's over it, but trust me, there's nothing right there. 1, 2. That's our to carbon B. 3, that's not a carbon on that end, so it's not going to show up. 1, 2, not a carbon. 3, we should have both of the methyls are showing up as the same signal because they're identical.
What?
I could see that. So now let's look at D. So D, 1 bond, 2 bonds, not a carbon. 3 bonds, carbon. 1 bond, 2 bond, 3 bond, carbon. So carbon C and carbon D should both be coupled to proton B. Boom, boom. Exactly what we expect. So 1, 2, 3. 1, 2, 3. All right, so is it super useful at this stage for me to just give you a 2D NMR, especially in HMBC, and say, what's the structure? No, but it can confirm what you think the structure is pretty reliably. Right, so when you think you have the structure right, you go through this process. You say, okay, proton B, what signals should show up? Does that match with what I see?
Furniture rental and clothes.
You like my bands?
I didn't recognize it.
We're talking about Fourier transforms today.
Oh, are you?
We're not actually doing them. We're just going to let the computer do them for us to do two-dimensional NMR.
Okay.
It's fun though.
Yeah. You should you calculate space physics.
Nothing.
I'm here to pull for more.
So I also thought about, small aside real quick.
Yeah.
Graphite is technically, it's not supposed to show up as having a band gap. It occurred to me as soon as you left.
Okay.
So you won't be able to measure it, won't be able to use it as a semiconductor. You might measure it's not a great conductor, so it might show up as a very small band gap. But if you got a true semiconductor like silicon, you might be able to get a better, or be able to do that experience where you vary the voltage and it'll get zero current, and then you get a conductor.
We have changed.
Okay.
Our study.
Okay.
But if we need to see if we have it, but.
Okay. Sounds good.
Yes.
Is also gonna talk to you about stuff like, because we had that class.
Club, science club.
Well, we were in lab, but it was science club. We had class. Just questions about like Marcelo. How did we put that on when we all leave and. Oh. And then will you maybe talk to Interest to get more logos to you? We did last time. I'm sure it's amazing and we love you so much.
Just a power broker.
With great power comes a lot of tasks.
Yeah, you're not really.
Sure.
Thanks, Atticus.
Yeah.
Right, so this looks like a mess.
Yeah, a little bit.
But again, if we already know the structure and we've already assigned A, B, C, D, E for protons and C, B, E, D for carbons, this should make sense, right? So B, the protons on B have a carbon 2 bonds away and a carbon 3 bonds away. So C and B should show up here, which is what we see, right? I'm not giving you the zoomed in version yet because I don't want to cover up any of this. C should also have 2 signals, right? Proton C, 2 bonds, 1, 2, 1, 2. So we should see B and D show up here. Boom, boom.
Why don't we see E show up?
Why don't we see E show up? Because remember, you have to count the bond for C. 1, 2, 3.
Yeah.
So you don't forget to count. That's why the figure always draws in the hydrogen so that you don't forget to count that as a bond. Right, so for B, 1, 2, that's C. 1, 2, 3, that's D. One, two, 1, 2. But 3 in both cases takes you nitrogen, which doesn't show up. You can also kind of, if we got to a less organic or less common organic molecule, if we did this with a fluorine, fluorine has 14 or has 19 nucleons, right? So fluorine shows up in NMRs really well. You can do a fluorine NMR. You can do this with proton here and fluorine here to see what's close to a fluorine. But in general, we're limited to only nuclei that have an odd number of particles in the nucleus, nucleons. Which is a useful limitation. Sometimes limitations can be useful so you don't get too much coupling. We don't want to see everything coupled to everything because then you can't actually tell anything what's going on. All right, so for D, one, two, nope, three, yes. So it should be show up as coupled to our ethyl or our methyls. One, two, yes. One, two, three, yes. So we should have three signals here for carbon, for proton B, C, B, and E. All right, and we're doing this by looking at protons and then translating it to the carbon NMR. You could do this the opposite direction just as well, but it gets really, really confusing if you aren't systematic with the way you approach it. And you should get the same information whether you go from carbon to proton or proton to carbon. So since we know the proton NMR is better, that's what I would always use as my baseline. Right? Start from your comfort zone and expand outward instead of starting with the one we know less about. And then just be consistent. Look at the protons to the carbons, not carbons to protons.
So for E,
Mm-hmm.
we're saying it only has two. But like when you go back to the zoomed out map.
No problem.
What about this one?
So we haven't looked at E yet. We've looked at something coupled to E. We haven't looked at the protons for E yet. We looked at what's coupled to the carbon for E. Right, so proton D will show up as coupled to carbon C, carbon B, and carbon E. Proton, one bond, two bonds, not a carbon. Three bonds, carbon. Three bonds, carbon. So because there's two identical carbons that are where the proton on one carbon is 2 to 3 bonds away from the carbon, it'll show up as coupled with itself. Because this is the only carbon that's symmetrical to anything else.
So then it's like, no one that chocolate. Too far from secrets. Oh,
It's the end of the slideshow. Oh, you mean this little guy? I wouldn't worry about that little guy. That's just noise.
it was when you look at the smaller one, was there all that? It's.
Yeah.
Hmm. Then look like my house.
Yeah, you're right. That is confusing when it's like that. When you zoom in and you see how much smaller it is compared to the others. But
It's four, right?
it definitely should not be showing up. So I would not, and especially when we see the zoomed in version, we see how tiny it is. Ignore it. All right. So what are we going to do with this? I'm going to print you out some spectra in a worksheet, and you're basically going to go through this process with some other spectra. Same COSY, HSQC, HMBC for a couple of things, and just create your own translating dictionary.
Okay.
And map out what makes sense. Right. So this is not one where I'm going to give you, here's some spectra. What is it? It's not that type of lab.
Yeah.
There's probably people out there in the world that can do that. I'm not one of them. I don't expect you to be at this level either. I want you to be aware of it so that